Hey everybody, it's back, gas stoichiometry. So, our gas stoichiometry happens to be target 10.9, which is our last target before our unit test. And so, the way that gas stoichiometry works is it kind of depends on standard temperature and pressure. Now remember, standard temperature is 273 Kelvin, standard pressure is 1 atm, and 1 mole is equal to 22.4 liters. So this value is something new that we are kind of adding in, and so we can use it as an extra way to kind of maneuver through our gas unit. Now one thing that is important though is 1 mole is equal to 22.4 liters, but that's only at STP. So if we're not at STP, that is not true. And so anytime it says at STP, we're allowed to use 22.4 liters. If it doesn't say at STP, though, it is a little bit different. And so our first example is a sample of argon gas has a volume of 3.45 liters at STP. And so that first part is that 3.45 liters would represent our volume. STP tells us we know our temperature is equal to 273 Kelvin. And our pressure would be equal to 1 atm. And so our question is, what is the mass of the argon? Now, there's two ways that we could go through doing this. The first way would be with our ideal gas law, which remember is PV equals nRT. Now, if we're going to go that way, we would have 1 as our pressure. Our volume, 3.45 liters, is equal to our number of moles first, times our ideal gas constant, 0.0821, and then multiplied by our temperature of 273. Now, if we go through and solve for our number of moles here, we should get 0.154 moles of argon gas. Now, since it does say what is the mass of argon, hopefully that reminds us that it's asking for a gram value, not a number of moles. So if we're asked for a gram value, our last step would then be to convert our 0.154 moles of argon to grams. So we set up our fraction as what you want over what you got. In this case, we want grams. We got moles. And remember, anytime we're converting from moles to grams or grams to moles, the 1 always gets paired with the mole value. And then our molar mass, or our gram value, comes from the periodic table. So we look at it, we see that argon is 39.95 grams, and so when we plug this in, we should get 6.15 grams of argon. Now the other way that we could do it, which is using our molar volume, or the 1 mole is equal to 22.4 liters, would be the other way that we could go through and solve this question. So since we're at STP, we can essentially set up a conversion knowing that 3.45 liters is the amount that we're starting with. And so we set up our conversion. It would be our 1 mole over 22.4 liters. And then we'd multiply it by our molar mass, because remember, our liters should cancel here. And so since we want grams, we got moles. We set it up. And remember, the 39.95 comes from our periodic table. And so we should have 3.45 divided by 22.4, then times 39.95, which should give us 6.15 grams of argon again. And so either way we go through solving this question, we end up with the same answer. So our next question, a sample of hydrogen gas occupies 15 liters at STP. What volume will the sample occupy at 22 degrees Celsius and 2.5 atm? And so one of the things that is kind of avoided in this question is the fact that it doesn't give us a value for the number of moles. But since we know that it occupies 15 liters at STP, we can solve for our number of moles. And so if we go through and do that, we should do 15 liters, and then we'd multiply it by our it would be our 1 mole over our 22.4 liters, which should give us 0.67 moles of our gas. Now with that 0.67 moles of gas, we can now go through and plug it into our ideal gas law, or PV equals nRT, because we know 22 degrees Celsius and 2.5 atm. Now when we look, if we kind of make our list of values, remember our pressure is changed to 2.5 atm. Our volume is what we're asked to solve for. The number of moles we know is 0.67 moles, and our temperature is 22 degrees Celsius, but remember, we don't use degrees Celsius, instead we use Kelvin, so we convert it by adding 273 to give us 295 Kelvin. And so now we can plug our values into our ideal gas law, so we should have 2.5 atm times our unknown volume is equal to our 0.67 moles times our ideal gas constant, remember that's 0.0821, times our temperature, 295 Kelvin. And so now as we go through, do a little bit of fancy algebra, we should get a volume of 6.49 liters. So our next question actually gets into more of the stoichiometry side, where we begin kind of using it in terms of reactions. And so our first question, or our reaction here, is nitrogen gas plus hydrogen gas produces ammonia. Now our first question says what volume of H2 will be consumed when 7 moles of nitrogen completely react at STP. So since we're given 7 moles of nitrogen, one of our first steps in trying to go from nitrogen to hydrogen should be looking through or using a ratio. And remember, our ratio comes from the coefficients in our balanced reaction. And so we should have 3 hydrogens for every 1 nitrogen. And so when we plug that in, that tells us that we have 21 moles of hydrogen gas. So we know at least the amount of hydrogen gas that's going to be consumed. Now we can go through and use our molar value, or our molar volume, to then figure out the number of liters. And so remember, it says that it's 22.4 liters for every 1 mole of gas. And so we should take 21, we multiply it by 22.4 liters, and we should get 470.4 liters of hydrogen gas. So our next question, if a reaction produces 60 liters of ammonia, what volume of N2 will be consumed at STP? So this one's a little bit different because we're starting off with liters of our product, and we're trying to figure out how much of our reactant we end up using. And so if we're starting off with our 60 liters of NH3, our first step should be to convert it to a number of moles. And so we set it up as 1 mole over our 22.4 liters. Now that at least gets us to moles of NH3. Now remember, if we have moles of NH3, we can do our mole to mole ratio. And so when we look, we're going from NH3 to N2 this time. We look at our coefficients and we see that there's 1 nitrogen for every 2 ammonias. And then our last step, because it's asking us for the volume of nitrogen, would be to convert back to our volume. And so we would multiply finally by our 22.4 liters for every 1 mole. Now when we plug all this in, we should get that we end up using 30 liters of nitrogen gas. And so our next one does get a little bit trickier because we're given a reaction, phosphorus plus hydrogen produces phosphorus trihydride. Now, one thing that is kind of a little different, though, is this is not balanced. So we do need to balance our reaction. And so to balance our reaction, we look for phosphoruses, only 1. So let's put a 4 there. Now, after we add that 4, we have 12 hydrogens as our products. So we need 12 in our reactants. So we add a 6, and now we're all balanced. And so our question, what volume of hydrogen at 27 degrees Celsius and 1.25 atm is required to react with our 5.65 grams of phosphorus? Now, when we go through, hopefully one of the things that we notice is the fact that we're starting off with a gram value of phosphorus, but we're asked about hydrogen. So one of the things we want to start with is 5.65 grams of phosphorus, or P4, and we want to convert this to our number of moles. Now, when we do that, we should have 1 mole over our molar mass, but remember, since it's phosphorus 4, we actually have to multiply the value we get from the periodic table by 4. And so that gives us 123.88 grams. And so after we get our moles of phosphorus, our next step would be to look at converting from moles of phosphorus to moles of hydrogen gas. And so when we look at our balanced reaction, we hopefully see that there are 6 hydrogens for every 1 phosphorus. Now by doing this, this does give us a number of moles for hydrogen. And once we plug all of this in, we should get 0.274 moles of hydrogen. Now, since we have this mole value, when we think about the other things that we have for hydrogen, it tells us we have a pressure of 1.25 atm, we have a temperature of 27 degrees Celsius, which remember we should add 273 to, which would give us 300 Kelvin. And then we just figured out we have a number of moles of 0.274. Now with all this information, the last thing that we're missing is our volume. And so we can solve for our volume using our ideal gas law again. So PV equals nRT. And so if we're going to use our ideal gas law, we should have our 1.25 atm times our unknown volume is equal to our 0.274 moles times our gas constant, 0.0821, multiplied by our temperature, 300 Kelvin. And so now we just go through and solve for our volume. And so our volume, once we plug it all in, is 5.4 liters. And so with our little bit of stoichiometry at the beginning, we were able to first convert our grams of phosphorus to a mole value for hydrogen, which we then use in our ideal gas law. And so our last question, we have calcium carbonate goes on to produce calcium oxide and carbon dioxide, and we're already balanced for our reaction. Yay! So since we're already balanced, we can just get straight into doing some calculations. So our question, we have 6.25 grams of calcium carbonate are heated. What volume of carbon dioxide would be produced when collected at 22 degrees Celsius and 1.05 atm? So our first step would be looking at our 6.25 grams of calcium carbonate, so CaCO3. Now, our first step would be to convert it to moles. And so we should have 1 mole of calcium carbonate over our molar mass for calcium carbonate, which happens to be 100.09 grams. Now, after we get to moles of calcium carbonate, our next step would then be to go from moles of calcium carbonate to moles of carbon dioxide. Now, when we look at our balanced reaction, we should see that there's 1 carbon dioxide for every 1 calcium carbonate, which means that our 6.25 grams of calcium carbonate would produce 0.0625 moles of carbon dioxide. Now, after we have this moles of carbon dioxide, when we look at the other values that we have, our pressure we're given as 1.05 atm. The volume happens to be what we're trying to find. Our number of moles for our carbon dioxide, we just figured out was 0.0625. And our temperature, we were given 22 degrees Celsius, which we add 273 to give us 295 Kelvin. And so once we go through and plug it into our ideal gas law, or PV equals nRT, we should have 1.05 times our unknown volume